know not all digits in a measurement are significant, we have to determine what values are and what aren't. Okay, so what's the rule for when we use an instrument to measure? You remember how we talked about when we use an instrument like a meter stick or a graduated cylinder, what do we do when we're reading that instrument and we're trying to determine what that measurement is? Yeah, that's right. We read what it's given, right? Read to what it's given, and then we estimate one more digit. So in this example, the meter stick is used to record a pin, and the measurement is 14.3 centimeters. That means for sure they knew it was between what and what in terms of whole centimeters? Yeah, they knew it was somewhere between 14 and 15, right? Those are for sure. And then that 0.3, that's the estimated digit, right? We're always assuming the last digit is estimated. So that 0.3, they knew it was somewhere between 14 and 15. They thought it was closer to the 14 side, right? So they picked that 0.3. So in this measurement, and in this particular example, all three of those digits are valid because we know we read two of them for sure, and that last one is an estimate. So at least we put some thought into it, is what we're saying, right? That's a valid digit. We knew two for sure, and we estimated the last one. Okay, so in this example, all three are valid. So that's what we're talking about. The only questionable digits really in numbers are when zeros get involved, right? If we have really, really small numbers or really, really big numbers, we can get zeros on either end of our digits, and that can be where things are considered not significant. Okay, so the rules about significant figures have to do a lot with zeros. Okay, and I'll talk about that here in a second.
So if there's a 0 after the 3 in that example, then 14.3 is still significant, but the 0 is not?
The 0 actually would still be significant because it's saying we think it's exactly 0.30, right? So that falls under one of our rules. But yeah, good question. Okay, so there's a set of about 5 or 6 rules for significant figures. Okay, so I'll put them down and we'll start talking about them here. First rule is all non-zero digits are significant. So any digit that is not a 0 is always considered significant. In this example, 436 milliliters. How many significant figures are in that measurement? 3, right? All non-zero digits, right? So this is 3 Sig Figs. Okay, so you will have to be able to identify how many significant figures are in measurements. Okay, and then we're going to talk about math rules that go with it. But first and foremost, our goal is to determine how many Sig Figs are in certain measurements. Okay, so that's 3. Next rule is where zeros start to get involved. So zeros to the right of digits, that's really important, to the right of digits after the decimal point are considered significant. So of those 3 measurements, right, they all say 12 centimeters. Which is the most exact of those measurements? The first, second, or third? The first, right? It's got 2 decimal places. That means we know this one was for sure, and we estimated this one, right? Like on the next one, we know it's 12. We think it's exactly 12.0. On the last, we don't know it's around 12, but we think it's around 12, right? That's the difference between these things. So the number of significant figures allows us to look at which is more of an exact measurement, okay? So these zeros are to the right of digits after the decimal point, and so they're significant. So how many Sig Figs do we have in our first one? 4, 3, and 2, right? This one has 1, 2, 3, 4, 1, 2, 3, and 1, 2. Okay? Same with one that looks like this, 18.400 inches. Right? How many Sig Figs here? 5. 1, 2, 3, 4, 5. Right? It's telling us we think it's exactly 0.400. Okay? So the fact that they are to the right of the decimal point and to the right of digits, that's really important. Okay? So to the right of digits after the decimal point, are significant. Okay, questions so far? Okay. Zeros that are in between digits are considered significant. And I think this rule seems pretty common sense because a zero in between digits is just part of the number, right? It's just part of the actual measurement itself. So an example would be 402 milliliters, right? That zero was just part of the number, right? So that is significant. So how many sig figs do we have here? 3. 1, 2, 3. How about this? 402.010 milliliters. 1, 2, 3, 4, 5, 6, right? So since this zero is to the right of the decimal point after digits, it's significant. That means anything between there is significant as well. Okay? Questions? All right, very good. Now here's where it gets a little bit different. Okay, zeros to the left of digits. So zeros before any digits start are non-significant. Okay, they are what we just consider to be placeholders. They're not helping our measurement at all. They're just showing us how small the number is. So zeros to the left of digits before any digits start are non-significant. It makes no difference whether they are before or after the decimal point. If they are before any digits start, they're non-significant. Okay, so in this example, how many sig figs do we think we have?
4.
How many of you think 4? How many of you think 3? How many of you think 2? 3. 1, 2, 3. Okay, and this is why these zeros are to the left of digits before they start. So they're non-significant.
How do you write that as a measurement?
This would be like 0.0860 centimeters, right? And if the reason that's non-significant is because we could just write this as 0.860 millimeters or 860 micrometers or whatever the next one is. You know what I'm saying? Like we could always alter our units to get rid of those initial zeros. Does that make sense? That's why they're non-significant. There's no reason for them to be there. They're just placeholders. They're just showing us how small it is. Okay? So those zeros to the left of digits are non-significant. Let's try another one here. 0.4102. How many do we think? Hold up. 6. 1, 2, 3, 4, 5, 6. I would agree. Okay, this is non-significant. Okay? Because if it were in centimeters, we would just move it over one place and it would be in millimeters, right? And that zero would go away.
So there was a 0 before?
Determining significant figures is digits used in scientific notation or shown in scientific notation are significant. Okay, digits visible or digits used in scientific notation are significant. Okay, so we're going to dive into scientific notation a little bit more today, but here's what most should look like. There's an example of something written in scientific notation. So in scientific notation, if this exponent is positive, that means the number we're trying to express is larger than 10. Okay, if the exponent is negative, the number we're trying to express is less than 10. Okay, so the reason we use scientific notation written like this, it allows us to express really big numbers and really small numbers in a much more manageable setting, right? Rather than 2, 4, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? Without all those zeros. Okay, there's no need for us to write that many, so we don't. Okay, so in this scientific notation, any of these digits right here are significant. Okay, so 1, 2, 3, 4. Okay, so as long as our scientific notation is written in the correct form, all of these are here visible are significant. We don't care about the expanded number at all. right? We don't care how many zeros are tacked onto the end of the real number. We care about what's visible in scientific notation. Okay? So if my scientific notation looked like this, how many sig figs? 2. 1, 2. That's it. Okay, we don't care about the times 10 to the 8th. We care about those values there. Okay? We have all these rules for determining what digits are valid or not, right? Significant or not. But some numbers are what we consider ambiguous. Okay, this is a word you need to be really familiar with, ambiguous. Which means we don't know how many significant figures are in that measurement. We aren't sure. Okay, so I'm going to show you how to identify an ambiguous measurement. Okay, an example of an ambiguous measurement is 120,000, or 10, or 200, or 1,000, or 70. Can you see what's in common with all of these examples of ambiguous numbers? What's in common with all of these? They all end in a 0, and they have no decimal point, right? So we don't know how exact these values are. We don't know, is it around 120,000? Is it 119,000? It's rounded up. Is it exactly 120,000, 0.000, right? We don't know because there's not enough information there. Okay? So when we see an ambiguous number, if I would ask you how many sig figs are in this number, you would just write ambiguous, right? And you can just write like that. You can't tell me how many there are because you don't know. Okay? So this is how we look at it. These are what I call trailing zeros. Okay, so if a number has trailing zeros with no decimal point, that's considered ambiguous. We aren't sure how many significant figures there are. Okay? Do you know how we could go about fixing an ambiguous number? Because if you give me an ambiguous number like on a homework assignment as one of your answers, right, that's a problem. You should never give me ambiguous numbers, I hope. Okay? So how could you fix an ambiguous number?
Could you just add 0.0?
Yeah, you could add 0.0, right? So if I wanted to fix this, I could add a decimal point, right? If I know it's exactly 120,000 and I wanted to fix it, I could add a decimal point. Okay, that's if I'm allowed to have 7 significant figures, right? That gives me 7 sig figs. What if I'm only allowed to have 3 significant figures? How could you change it? Yeah, I could put in scientific notation. 1.20 times 10 to the 6th, or 5th, my bad, not 6th, 5th, right? 1, 2, 3, 4, 5. Okay, so now I'll kind of go into why would we have limitations on how many sig figs we have? Why would we only be allowed so many digits? Okay, there's rules that go into the math with significant figures. Okay, let's do a couple more practices on identifying numbers of sig figs, and then we'll move on to the math that goes with it. Okay? So, I'm going to give about 4 or 5 numbers up here. You're going to tell me how many sig figs are in each.
Do I have to write it down?
Yeah, you can write it down on your notes, or I don't care. It doesn't matter. If you want to make examples in your notes, you can put them up there. Okay, so there's 5 numbers up here. I want you to give me the number of significant figures in each of those. Okay, so on the first number, 398.010, how many sig figs do you think? 6. 1, 2, 3, 4, 5, 6. I agree. Okay, why is this 0 significant? To the right of digits after the decimal point, and why is this 0 significant? In between. Good. Okay, how many do we have in this value? 2. Is this one ambiguous? No, why not? Yeah, no trailing zeros. Okay, good. What's number 3? Ambiguous. Okay, so don't tell me 2 or 3 or 1 because we don't know. Right? We don't know, is it around 100? Is it exactly 100? We don't know, so it's ambiguous. Okay, and you can just write A and B. You don't have to write the whole word. Okay, next one. 125.74. How many? 5. Good. No zeros in there, so it should be easy. Okay, and the last one, 6.42 times 10 to the 18th? 3. Good. How many of you went 5 for 5? Anybody go 5 for 5? Good. All right, very good. Okay. So now we're going to talk about why there is limitations as to how many significant figures a measurement could have. Okay? First, your limitation comes from how exact your instrument is. Right? If my instrument is measured to the whole number, then I only get 1 more decimal place, right? So that tells me that limits me a little bit. But when we perform math operations using measurements, so if we add our measurements together or we multiply our measurements or divide, whatever we're doing, if we're adding or subtracting or multiplying or dividing those measurements, we have certain rules that we have to follow. Okay? So, here's the rules, okay? Adding and subtracting first. So these are rules for adding and subtracting with significant figures. You do the math first, then round your answer to the least, and I'm going to rewrite this so it helps us a little bit, least number of decimal places. Then round your answer to the least to correspond to, or just you could just say to the least number of decimal places. So here's a little example problem for us underneath. Okay? Out of these measurements, let's just say before we do any math, out of the measurements up here in this problem, which is the most precise value involved? Which is the most precise value? Good, 13.416. So why do you say that's the most precise? It has 3 decimal places, right? So that means we could read pretty far on our instrument and we estimated 1 more. So that's the really precise value. Which is the least precise in value involved? 11, right? Because it has no decimal places. So we think it's around 11, right? So when we add these numbers, go ahead and get your calculator out. Just add them in your calculator. What did we get for the raw answer? Just when you added them together, what was our raw answer? 67.516. Okay, do we all agree there? Yeah. Okay. So here's the thing with math with significant figures. Our answer can be no more precise than our least precise value involved. Okay, our answers can be no more exact than one of our measurements. So what's the least precise measurement? What did we decide? 11. And how many decimal places does 11 have? None. So that means we have to round our answer to have no decimal places because it can't be more exact than one of our measurements. So how do we round this to a whole number? 68. And whatever our units are would be tacked onto there too, but I didn't put units. Okay, 68. So that kind of stinks, right? Because we had a kind of exact measurement right here, but since one of our measurements had no decimal places, that makes our answer much less precise than we would like it to be. Okay, so that's how it works. Your answer can be no more precise than one of your measurements that goes into it. Okay, so when we add and subtract, we look at number of decimal places. That's important. Like write that again or put it in color or highlight it, whatever. But add and subtract equals decimal places. That's what you're looking at. Okay? Because our next one, multiplying and dividing, we just did an example there, so we don't need to do that one. Multiplying and dividing, we do the math, then we round to the least number of significant figures. We're going to do the math, then we round to the, I'll rewrite it so it's a little easier. To the fewest number of Sig Figs. Okay, so when you multiply and divide two measurements, you do the math, and then you round your answer to the fewest number of Sig Figs based on your measurements. If we're multiplying and dividing, we need to look at fewest number of Sig Figs. How many does their first measurement have? How many Sig Figs? 1, 2, 3. Good, it's got 3. How many does our second measurement have? 2. So that means our answer can only have how many significant figures? 2. So how do I get this to be 2 Sig Figs? Yeah, I just round up to 29. Okay, I could also do this, 2.9 times 10 to the first. Scientific notation always works because you can always put as many digits in there as you want, but scientific notation is pretty unnecessary in this case. Right, scientific notation is kind of unnecessary there. Okay, but 29 is our final answer there. What questions do we have with multiplying, dividing, or adding and subtracting? Okay, so I'm multiplying and dividing first, and then adding and subtracting second. Go ahead and do these on your own. 3, maybe. 319.7. And how many significant figures are we allowed here? 2. So, how do we put this into 2 Sig Figs? Good. Evan, what'd you have for your final answer?
3.2 10 times the second power.
Perfect. 3.2 times 10 to the second. Because if I round this up to 320, right, does this give me 2 Sig Figs?
No.
What does this give me? No. It gives me an ambiguous number. Right, that would give you a big frowny face on your paper. This is ambiguous, which is no good. Right, so the way we fix an ambiguous number is we put it in scientific notation. Okay, so that's how we go about doing that. Even if we would have been allowed 3 significant figures, 320 wouldn't have worked. It's ambiguous. Right, so we would have done this, 3.20 times 10 to the second. If we would have been allowed 4, then we could have done there. Actually, if we would have been allowed 4, we would have just left it like that. Right? So it's all dependent upon how many Sig Figs you are allowed. Okay, you put it in scientific notation. Okay, so on our addition and subtraction, we look for our least precise value, which could have been either of these, right? Because they had 1 decimal place each. Our answer has to have 1 decimal place. We round up on a 5 and down on a 4 or anything below, right? Does that rounding make sense? A 5 or above rounds up, 4 or below rounds down. How many of you got both of those? Okay, both of those correct? The first one stumped a lot of people? Okay, that's all right. That's all right. All right, good. So, scientific notation follows this format. M times 10 to the n. M times 10 to the n. This value must be greater than 1 and must be less than 10. Okay, so I'm just going to put in an X. Okay, or I can put in an M there, I guess. Okay, so that M value has to be between 1 and 10. Can't be smaller than 1, cannot be greater than 10. The n value here has to be a whole number. That's the only rule for the exponent. Right? We can't have fractional exponents in scientific notation. Okay. Has to be a whole number. That's the only real rule there. It can be negative, it can be positive, it can even be 0. Just can't be a fraction. Okay? But this is the part that's really important. Has to be between 1 and 10. We'll see people try to do 43 times 10 to the something, right? That doesn't work because 43 is not between 1 and 10. Okay, so it's got to be there. The reason we use scientific notation, it gives us freedom when we want to express numbers in a specific number of sig figs. Okay? It allows us to express really big numbers and really small numbers in a more manageable sense, and it allows us to adjust the number of significant figures. Okay? So we'll just look at an example here. 125,648. And I want to try to put it into scientific notation. And how many sig figs do you want to use? Between 1 and 6? 2. I heard 2. We'll do 6 in a minute. Scientific notation with 2 sig figs. Okay, that's what we want to look at. Oh yeah, you're right. It does have 6 in the number. Okay, but we're going to put it in scientific notation with 2 sig figs. That's our goal. Okay, so if you think you can start working it yourself, do it, but I'm going to show you how. So scientific notation, the number has to be between 1 and 10, which means the decimal needs to go between what 2 digits? Needs to go between here. Where's our original decimal point at? At the 8, right? So we're moving it 1, 2, 3, 4, 5 places. Okay, so that means it's going to be times 10 to the 5th. This number is positive when the number we're trying to express is greater than 10. Is 125,000 greater than 10? Yes, so it's to the positive 5th. We can only have 2 sig figs. So that means we need to have 1.3 times 10 to the 5th, right? This 5 rounds up. So our 1.2, right? We originally would have 1.2 times 10 to the 5th, but since we've got a 5 there, we round that up. So we have 1.3 times 10 to the 5th. Does that make sense?
The exponent is the number of decimal places you moved.
That's right. The exponent is the number of places we moved it. So if you punch in your calculator 1.3 times 10 to the 5th, right, you get 130,000, which is, you know, what we're expressing there. We had to round, which is unfair. We're taking away some of our exactness. But yes, the exponent is the number of decimal places we moved. And some people try to memorize, if I move it left, it's a positive. If I move it right, it's negative. Don't do that, right? If it's larger than 10, we have a positive exponent. If it's smaller than 1, we have a negative exponent. Okay? So let's do this same exact number with 4 sig figs. Okay, same exact number. Let's put it into scientific notation with 4 sig figs now. Okay, we said our decimal place has to go between the 1 and the 2. It's still times 10 to the 5th. Right, that doesn't change anything. But what changes is how many numbers can go right here. So if we're allowed 4 significant figures, it would look like this. 1.256. Right, and that gives us a lot more exact picture of the number we're trying to portray. Right, if you put that in your calculator, 1.256 times 10 to the 5th, we get a much closer answer to our exact number than we did when we had to round to 1.3. Okay?
Can you do it one more time?
So let's do it one more time. We'll put it with 3 sig figs this time. Okay? So with this same number, let's say we want to use 3 sig figs. We know the number has to be between 1 and 10, so our new decimal is going to go here. Our original decimal is here. So 1, 2, 3, 4, 5 places is the number of places we're moving it. So 10 to the 5th. If we need 3 sig figs, that's 1, 2, 3. So 1.2 what? 6. This is going to round this up to a 6.
So why does the decimal go up to the 1?
Because the number that has to sit here has to be between 1 and 10. So we need only one whole number here.
Okay.
Okay, does that make sense? Okay. Questions? Okay. Try this one on your own. 124,215 in scientific notation with 3 sig figs. That's pretty close to the number I just made up in my head. All right, what you got? Times 10 to the what? Do we agree? 10 to the third. What should it be? To the fifth. Okay? This has to go here, 1.24, right? That would give us a number between 1 and 10, and then we can move it to our original decimal place. Right? So we moved it 5 places. Okay? Now we're going to work on expanding numbers from scientific notation. So let's say I give you this number, 4.03 times 10 to the negative fourth. And I want you to put it just in regular terms. Just write it out as a regular number with zeros. Okay, what's the negative 4 tell us? It's going to be a big number or a small number? It's going to be a small number. Okay, so what we do is write out 403, right? Here's our original decimal place. We want it to be smaller than 1, so which way should we move the decimal? So we move it 1, 2, 3, 4, and then we fill in with zeros. Okay, so our final answer is 0.000403. And how many sig figs does that still have? 3. Right, so scientific notation doesn't change the number of sig figs when you expand it out, right? These are non-significant because they're placeholders. Okay? Uh-huh.
Is there a name for it? Like scientific notation is the way to write it that way. Is there a name for those, or is it just like regular?
Like an expand. You would just say expand these from scientific notation or something like that. Yeah. Yeah, you got about 1 minute. Okay. Let's put this number into scientific notation. Let's put it with 3 sig figs. Okay, so we'll go into scientific notation with 3 sig figs. Okay, so if I need my number to be between 1 and 10, where does the new decimal place, where does it need to go? Between what 2 digits? Between the 1 and the 6, right? That would give me a number between 1 and 10. Okay, that's how we're determining that. And we have to move it 1, 2, 3, 4, 5, 6, 7 places to get back to our original. So it'd be times 10 to the 7th. Is it to the positive 7th or negative 7th? Negative, because it's a less than 1. That just leaves us with 1.64. Okay? Does that make sense?